opportunity, and thank you to everyone who is participating. It's a great pleasure to be part of ICAR and CCPO and give this virtual seminar. Maybe one of those days we'll do in-person seminar series, who knows. So the focus of my talk today will be on recurrent flooding on roadways. That's what I'm most interested in, transportation systems and safety, driver behavior. So I'll be looking at the flooding problem from a different angle. I know, throughout this seminar series, there have been a lot of talks on resiliency, sea level rise, forecasting, and the impacts of all of that on the urban landscape. But my focus will be specifically on the transportation side and mobility, safety, driver behavior, roadway capacity, traffic flow. So as Tom said, we are no strangers to flooding, being in Hampton Roads in Norfolk, and ODU campus specifically. There's a picture I took a few years ago just to explain the type of problem we are looking at. So most of you might have faced this dilemma, whether or not to go through some partially flooded roads or turn around. And it's not an easy decision because it's really difficult to judge how deep the water is. And a lot of people play safe, just turn around, as you see in this picture, and some don't. Maybe it's a function of your car and how confident you are about your prediction of the water depth. So what we want to do is help the driver ultimately and help the cities manage traffic by providing better information. But this is a challenging issue. The fact that we have large-scale networks and the flooding could happen in lots of places. It's not just one single location. So instrumentation is challenging. So we cannot just put, sensors to measure flood level, water depth, and that could be very costly. So alternatively, we are looking at image-based approaches using computer vision, AI, machine learning to extract valuable information from already available data, like video data, that a lot of cities have cameras installed in lots of places. And the question is, can we leverage that? So the work I'll be presenting is mostly part of a current NSF project, but we kind of started this work even before that. But the bulk of it is under the project listed here on the slide, which we call Scalable Modeling and Adaptive Real-Time Trust-Based Communications Smart Sea System for Roadway Inundations in Flood-Prone Communities. It's a kind of long title. And I want to acknowledge my collaborators. Kaan Iftikharuddin from Electrical Engineering is the PI from ODU. And then we have John Goodall from UVA, myself, Naveed from Civil Engineering, and Jing Cheng, who used to be at ODU, now she is at Rice University. So the problem or the hazard we are studying is recurrent nuisance floodings. Even though some of the techniques, methods could be applicable to major flooding, but our main focus is recurrent flooding. It has its own kind of unique aspects we have to take into consideration. And our focus is to leverage machine learning, leverage video data, image data to understand the depth and extent of flooding on roadways specifically. And once we do that, then we will also study how this will impact traffic and what are the best ways to communicate this information to the drivers. Because there isn't really a lot of literature on this. It's kind of, flooding has been around for a long time, but, that's the fact that it's becoming more frequent is a newer side of the equation. So for that, we want to be effective in managing the system. So we don't certainly want to close the roads under any kind of flooding, right? If there's minor flooding, just a couple inches of rainwater or flood water on the roadways, that may not really warrant closing the road. So what is, how do we make all these decisions? What are the best ways to communicate such information to the driver? So I'll get into some of these and show you some of the results from our methods that we have been developing so far. So in terms of the outline, so I'll just give you a little bit of background on this image-based methods and some of the methods we built to estimate flood extent and depth on roadways. And then I'll show you what this means for traffic flow, like, how this will impact road capacity. And then at the end, I'll show you some videos that we collected and showing how drivers behave when they don't really have a lot of information on hand. Okay, so I guess we already kind of know what the problem is, but just to reiterate, this recurrent flooding is expected to become even a bigger problem. And we have seen these projections from NOAA and other agencies and researchers. Just to give you a highlight a number here, the frequency of these flood events in the Gulf Coast and Southeast Atlantic coast has increased over like 400 to 1,100% within the last 2 decades or so. So it's a dramatic increase, and unfortunately, it's expected to get worse. Right? These are our projections. So then, what are the implications? Right? What should we do about this? And that's where we want to focus on as engineers. Right now, we understand the problem, what the problem is. Now let's just talk about solutions. Right? So we don't really have a scalable, effective solution to monitor road conditions. So we don't know what the extent and depth of flooding is. We don't know whether the roads are drivable or not at any time t. Right? So now what we want to focus on is AI machine learning approaches and leveraging image data, and then just kind of going from there and looking at the applications. So when you look at the literature, in the last 1 or 2 decades, there have been a lot of work on machine learning, image-based methods, looking at image segmentation, the semantic segmentation approaches, where we want to separate flood water from the rest of the image, because that's useful, right? So we know like how much flood water we have in a given image that can potentially help for making a decision. And then the second part of the equation is understanding what objects are in the image, such as people, cars, and traffic signs. So using these objects, we could perhaps figure out or estimate how deep the water might be. And then there's we can use machine learning in general, just train them if we have a lot of label data. Label in this case could be like the depth of flooding for the different images. So you can, if you have sufficient data, you can train them, and they will learn. If you have sufficient data, then will help you make a prediction. There's another type of research in this area, which is have been around for a longer time, using remote sensing, satellite imagery. If you have topographic data from a LiDAR or other types of sensors, and then we can figure out the extent of the flood, overlay these, and then these two, like kind of intersecting these two types of information, the topography and the extent of flooding, then that could be another approach to figure out how deep the water is and the extent of the flooding is. But this, of course, having a satellite image may not give you enough resolution, enough accuracy for certain types of decisions that we are going to be talking about. All right. So the first topic I want to touch on is like the extent of flood. Given, let's say, a random image could be coming from like a social media image or just a random image from a website, can we just detect how much flood water is in that image? Can we accurately do that? This may sound maybe a relatively easy problem to some of you, maybe those who are in computer vision and have some background in AI machine learning, but it turns out that it's not as straightforward given the variety of images, the lighting conditions, the color of the water and the objects in the water. So it could be very complicated. Okay, so what we did is, this was my former PhD, did some work on this. He collected some data. At the time, we didn't have a lot of labeled images, so he labeled them by hand, basically segmenting where the flood water is for about 250 images. And then he trained certain models to figure out, whether we could solve this problem through these machine learning or AI techniques. Okay, so he applied more specifically 2 methods. One is these deep neural networks, what we call fully convolutional network. And then another method is superpixel-based segmentation, just to give you a little bit background on that. So take an image, look at these larger pixel sizes that are somewhat uniform so that you have a smaller problem to solve. And then you label these, you say, okay, this pixel is a flooded portion of the image, these pixels are something else. So then the computer can kind of, if you feed enough data, it will learn what is flood, what is not flood. So that's the main idea. That's one way to approach it. The second approach is a more common now with these deep networks and transformer networks, and every day we get almost every day we get a new type of development in the AI literature on these machine learning algorithms that are getting bigger and more sophisticated, and they have billions of parameters as a matter of fact. So then we can train them, or they are actually already, the ones we are using are pre-trained mostly. So we could just maybe train some portions of it that are relevant for us. So then these will help us segment the entire image at once because they have already been trained, and then we can assess, whether or not these tools are effective. Of course. So the thing with machine learning is that, as most of you probably know, the more data you have, the better these models learn. Okay? So the richer data, more variety. So they learn these complex patterns because they are very large models. They have billions of parameters. And then we measure how they perform in terms of these performance metrics, which includes precision, recall, F1 score. And here are the results for these 253 images that my student labeled by hand. And he applied these, I would call, more traditional method, where he handcrafted features. He extracted what would be an interesting feature to look at, and then applied a classification method. And then he used this FCN model, which is a deep neural network model. And then he observed that works better, which in a sense is easier because you don't really have to think a lot what features to use, what not to use. So it kind of extracts the features for you that are most relevant for the problem at hand. So we get about 90% accuracy. There are specific statistics here. If anyone is interested, I can certainly provide a paper. So here are just kind of more visual results. The table is still here. So yeah, the problem could be solved, but it's not as straightforward as one might be thinking. So just feeding an image, an arbitrary image, to an algorithm, no matter how sophisticated it is, does not guarantee that it will be very reliable. So we definitely see good performance here. The couple images on the left-hand side here, and then a couple images here. This is the input image, and then here is the result. Here's another one. So you see, in this case, we have perfectly still water, clear water, and very good reflection of the house and the surrounding. Then the model struggles, right? It's just difficult for the model to know what's a house versus its reflection. So, maybe, you need more data, more training and things like that. And this roof happened to have the same texture color as the floodwater almost. So the model got confused there too. So these are a couple of examples where it didn't work very well, but in general, we got at the pixel level, we got 90% accuracy. So that's the segmentation. So there is a lot of literature on this because nowadays we have a lot of images and a lot of labeled images as well. So there is still work going on. We try to push these numbers as high as possible. So, but the bottom line is that we could perhaps not for such complicated a random image situation, but if we have a camera at a specific angle at a specific location, the problem should be a lot easier to solve. All right. So now what we did is we said, okay, we took one of these models that were trained with large data of these arbitrary images from websites, and then apply it to a video that we collected recently, back in October, after Hurricane Ian passed, and we had the high tide events, king tides. So we got some flooding on Hampton Boulevard. I'll show you more of these videos or images as we go along. So on October 3rd, here's one picture, one image from the video camera. And then we said, let's apply this model and then see what happens. So, and the right hand, the image on the right is the answer. So the black parts are non-flood pixels. And then when you can see the image, the model thinks that everywhere is flooded except these dark places that you cannot see. Well, if you observe this image, you would, as a human being, would say that, okay, the flood is only right here. Like this portion of the road is flooded, the rest is okay. So if you are going to drive through here, maybe you can avoid, but use this other lane, right? Which is a little bit flooded. But the model, if you use the model, it says, the entire road segment is flooded because the model has difficulty separating water accumulation from wet pavement because it's still raining a little bit and pavement is wet, so it's really difficult for the model to separate the two. So then we said, okay, let's look at more traditional approaches to computer vision. So we said there are these edge detection methods where we look at a few images together, like a video. Since we have video, we look at how these as these vehicles are passing, we have a little bit wind perhaps, so we get these ripples on the water surface. So we can apply a filter edge detection algorithm to detect these edges, and that could help better locate where the flood water is. And now here's the result of that simpler algorithm compared to the deep learning. So it overall tells us that these areas we see, changes in these edges. Therefore, there must be flood water here. So perhaps we could combine, this method with deep learning, kind of study a little bit more in depth to better locate the boundaries of flood water. So we did that. And then we apply this to another image, like about 25 minutes later. So now we have more water on the road. So it's just the flooding is increasing. Now we have this much water on the roadway surface. And it seems that this edge-based method is capturing the flooding relatively accurately, I would say. So now we are still, this is not completed work yet. We just kind of started processing the videos, and our plan is to combine the strengths of deep learning, machine learning with these more traditional image processing methods to get a better handle on the exact boundaries and the depth of the water using this videos that we collected. So that's ongoing work right now. So the second problem that we need to solve is how deep the water is. So now, unfortunately, it's really difficult to tell how deep the water is from an image because the water, the color, it could be dirty water you cannot even see, and you may not necessarily know how the pavement is exactly. So because of those reasons, we decided to create synthetic data using these programs like Unity, Blender, maybe a couple other ones that can help you create these digital images that are easy to label because you are creating them, so you know what the labels are. For instance, here in the Unity environment, we create a city, we introduce some flood water. Since this vehicle is known in the environment, we know exactly what the labels are. So here's the vehicle body, these are the vehicle tires, so on and so forth. We can easily create tons of data. And then later on, we moved to this Blender environment, which has a component called MentaFlow, which gives you a more realistic representation of water movement, water dynamics, the ripples and the waves, things like that are a bit more realistic. Then we created this as well. We presented this work at the IEEE conference last year. So now using these images that we created, we said, let's try to solve one specific problem. Right? Given an image of a vehicle, more specifically a side view of a vehicle, perhaps the vehicle is parked or stopped at a traffic signal. We have some flood water on the roadways. Can we estimate how deep the water is using the vehicle as the reference here? And more specifically, we use the tires because, again, the problem we are studying is recurrent flooding, not catastrophic major flooding where the entire vehicle could be underwater. So the road could be still passable. So maybe you have a few inches of water, and let's see if we can predict that using the vehicle itself as a reference for us. So we did that. So we collected a lot of data. In other words, we generated these images in that synthetic environment. In addition to that, we grabbed images from websites and our own images we collected in Hampton Roads because we do have lots of flooding events here. So from these images, we pass them through these machine learning algorithms that detect where the vehicle is. It detects where the tire is. There's this specific model called YOLO, you only look once model that is pretty effective in detecting objects. So we detect all these parts of the vehicle, in this case, the tires. And then from these tires, we pass them through a method to extract the tire and like fit an ellipse essentially where the tire is. And then from that, once we have the ellipse that represents the tire, and we can locate where the water line is, this yellow line here in this image would be where the water line is. So we have the tire. So now with image-based methods, one of the challenges is camera calibration. To go from like a pixel to a dimension to an actual dimension is not necessarily very, I mean, it's possible, of course, there are lots of techniques, but there's always going to be some error. But if we do know the exact dimension of this tire, then we are just looking at the proportion of the tire under the water, then it's a lot, hopefully a bit more accurate estimation of the depth here. So here are the results or output from this pipeline we have, this machine learning models plus this optimization problem we are solving. So we are looking at the depth as a percentage of the tire. So we are assuming that the vehicle is known. So it's a sedan or a pickup truck or even a truck. So consequently, if I know even the make of model of the vehicle, and these days it's possible, the cameras are having better resolution, these models are getting more sophisticated. I've seen a lot of papers on where people try to get the exact make and model of the car. If you know the make model, so it's relatively easy to know the tire size. So then from these, since we know the tire size, we know what percentage of the tire is under the water, then from that, we can infer the depth of the water. So that's the overall idea. And these are some of the advantages. So because of the fact that we use the tire as a reference, we don't have to deal with camera calibration, which could get complicated and introduce additional noise to the process. And so here are results, just some samples and how we are doing the curve fitting or this ellipse fitting to the tire itself, and then drawing the line that indicates where the water surface is. And then we had these variations of the deep learning models that are, using different architectures to capture the features and extract useful information. So since there are multiple options, so we decided to kind of do a little bit of sensitivity analysis, so to speak. But overall, if you look at the results, we are observing that we have about 10%, this is like plus minus 10% of error. We are, if this is acceptable, so the results are going to be reliable enough, perhaps, if you think that this 10% error is good enough for the application. So this last model tends to have like a little bit better distribution of the error around 0. So the thing is that these results are for individual measurements. If you have a lot of samples, let's say a lot of vehicles passing or stopped, and you can extract data, you average over time, then the error will be much lower than what we are presenting here. So the bottom line is that using this approach, if you have such data and you can use these vehicles as a reference, then it seems to be working relatively well. All right, so the next thing I want to touch on is what happens to the traffic flow in general. So if you have some flood water on the roadway, obviously we have too much flood water, let's say 10 inches or so, then they close the roads, so we have zero capacity, zero flow. But we are interested in, again, this like between, fully open operational road versus closed road, this gray area where we still want to maintain some operation, like keep the road open, but also monitor, like as we are approaching this, critical level where we need to shut down the road. So in this interim, what happens, like how much flow we can accommodate, what is the maximum capacity per lane or for the roadway segment. So when we do a literature search, unfortunately, there isn't much work on this, and mostly due to lack of data, empirical data. So we don't have a lot of video and data where we collect, traffic flow characteristics under partially flooded roads. Consequently, there isn't really a lot of information out there in the literature. Okay, so we installed the camera on Hampton Boulevard on September 30th last year, and the camera was there for about an hour. So we were observing at that day, I think it was a Friday afternoon. So we had relatively heavy traffic volume, and we had a substantial amount of flooding. on that roadway segment. I'll show you the map exactly where this installation site is on the next slide. But here we are seeing that, so vehicles are trying to pass through here, and we measured the flood depth at the curb. It's about 10 inches, but here in the middle of the road, it's less, maybe 7, 8 inches, maybe 6, 7. Kind of varies where you are exactly on the road. And then we measured, like we essentially counted these vehicles as they are going through these two lanes. We marked them as lane 2 and lane 1, and there's this lane 1, which is the closest to the curb, is narrowing, and then on the segment of the road, we go from 3 lanes to 2 lanes anyway, so this lane is not utilized a lot. Occasionally, we may see 1 or 2 trucks or larger vehicles there, but mostly we are focusing on these 2 lanes. And then we created this plot, which we call cumulative plot, and this is actually oblique plot because we remove the background, the flow, so that you can see the detail, as you see here. So for these 2 lanes, you are seeing how the volume is going up and down. So when it's up, that means like there's some flow. When it's going down, the flow rate is less than the background flow here. So that's not really important for our discussion at this point, that technical detail. But then what we did is we looked at this 1 hour plus period, and we tried to extract the time intervals where we have significant amount of flow, because we are interested in the capacity, like, what's the maximum possible flow we can process through this road, or drivers are able to go through this road. What is that rate? Okay, so then we looked at these segments as are highlighted here. For instance, for the green line, which represents lane 2, for a few minutes here, we have about 735 vehicles per hour. And then later on, we have 616, 626, 726, etc. So these are different flow rates that we observe, and these are sustained for a couple minutes to maybe a few minutes. So these are useful data points. So from these, we can infer what would be the maximum flow rate. Of course, one option is you can look at just this largest value, or you can average them out. But even if you go with the largest one, which is 735 here, so that's at a per lane level. But when you compare this number to a normal operation, for this segment, we don't have data, but if you were to collect, that number will be around 1,800, 1,900 vehicles per hour, so much higher than this. So we are seeing almost a 60% reduction from the full capacity to the 735 if you use this number. Of course, you go with the other ones, it's even less. So we are seeing a dramatic impact of the flood water on traffic flow of the capacity of the roadways. And this is expected, of course. So what we would like to do down the road is understand this impact as the flood water is receding or increasing, and see how flow dynamics change. Like, do we, what's the relationship? That will be very valuable for planning purposes for the cities, municipalities, so they can manage traffic accordingly. So as I showed you earlier in the presentation, sometimes we have just minimal water on the roadways. Vehicles do not even slow down when you have 1 inch or so, right? They just zip through. So what is the level? At what is the critical levels where people slow down, and that has a measurable impact on traffic flow. So we are working on this, but here is one case study where we have a certain level of flood, and we have these empirical data that tells us what the levels are. Of course, these are like at per lane level, but we are interested generally in the entire roadway capacity. Like, we want to know, like, in total, how many vehicles can pass through this segment. But we cannot simply add, as you might tell from this graph, these two lanes do not simultaneously accommodate these like 700 or 600 vehicles exactly at the same time. Consequently, when you add them up, your overall flow rate is going to be reduced because of the way the things are here. Like, drivers slow down, they line up. Usually, most of the time, it's just 1 lane operational because drivers want to be more cautious, and the middle lane is usually a little bit higher elevation. So mostly it's like 1 lane used at a time. So therefore, there is even more dramatic impact on the roadway capacity. And this is where we collected these samples. So the image here, the video we used for this data collection comes from a camera installed at point 1. And this is in Hampton Boulevard going northbound. This is the Larchmont Crescent, and up north is Surrey Crescent. So this camera was facing this way, towards the bottom of the page. And then on October 3rd, we installed another camera here at point 2. So we collected more data on October 3rd from like both of these cameras. So for several hours. So if you look at the tide gauge data, so October 3rd is here. So this is the peak, and this is where we have the video from. And then we have September 30th right here. So we captured, kind of the most severe flood level on Hampton Boulevard back in September and October. So the other thing that we wanted to study was driver behavior, like capacity of the roadway is definitely critical for system efficiency, for mobility, for managing traffic, but we also would like to study how drivers are behaving when there is this flood water on the roadway. So I'm going to show you a few videos that we extracted from the longer video. I think just visually it will be a lot easier rather than me explaining what's happening in the field. So there are a few videos that are explaining kind of this unique or peculiar behavior of drivers as they navigate through these roadway segments. For instance, one of the common things is that, like, as a driver, you are unsure as you're approaching this water, and you don't know how deep it is. And of course, we have some folks, they live and they've been in this area for a long enough time. They might have experienced this in the past. Maybe those are the ones that just proceeding through the road, but people might be coming from out of town or whatnot, and they may not really know what's going on. So we saw a lot of these cases where vehicles come in and they kind of hesitate first and observe what's going on, what other people are doing, and then they eventually drive through this flooded segment. And by the way, this is camera position 2, and we have deepest water is closest to the curb, and the leftmost lane has only a couple of inches of water. Right, so that's one type of behavior that's quite common. Okay, so the next one is, so here is a driver, like, is trying to go through it and drives all the way to the middle of the flood almost, and then backs up and kind of make a U-turn. So that's another, we've seen a lot of these as well. So I'll skip this one. So here's another case where another vehicle comes in the middle of the flood, and now we have kind of the peak flood level, and on the opposite side of the road, there's a vehicle that actually got stuck. I'll show a video of that later on. So this vehicle is like trying to decide, or this driver is trying to decide to go through it or not. Now the person saw another driver driving through, another one, and then eventually the person is convinced that it should be safe enough to drive through, right? Had there been no other vehicles coming in, perhaps the drivers would have just backed up and made a U-turn. But now, because of what the driver is observing, it's he's able to, I guess, drive through. So we can go to the next one. So here's a little more kind of dangerous behavior. Another driver approaching, hesitating, don't know what to do, and another cars come, and I guess it's a bit bigger vehicle, a pickup truck. It goes through, and then now the driver decides to go through, but they both want to use the leftmost lane, and they always had a collision right there. So it could be dangerous. So one of the things we could learn from this is that it would have been nice to perhaps close the 2 lanes and just open the leftmost lane, and there will be more orderly movement of traffic through this flooded segment. And here is a nice next one. So, we had a lot of vehicles going through, and let me actually mark this. So this vehicle right here on the opposite side of the road just got stuck. It was this Honda Civic, I believe, not particularly a large vehicle. So it just cannot go through, and it was on the leftmost lane. the water was too deep for that specific vehicle, whereas you can see that other vehicles are still progressing through the flooded segment. By the way, I apologize for the two vertical green lines. They are just part of a program. We could have got rid of them, but I hope you are, I didn't explain them earlier. So here's a more interesting type of behavior where we see that, sometimes, drivers, look at what other drivers are doing. In this case, we used to see a lot of traffic progressing through this segment, but now, like, a couple of vehicles first decide to make a U-turn, and then almost everybody after that, those two vehicles just decide to make a U-turn. It's kind of very strange social behavior. I guess in the literature, this is called herd behavior. In finance and other sector fields of research, there's certain models people use to study this kind of complex adaptive behavior. And then after these and few people go through, and then everybody else goes through. So it's a lot of complexities involved in how people drive through flooded segments. Next. All right, this is perhaps the most dangerous type of behavior we observe. So this vehicle decided to jump on the opposite side of the road and drive through there. So unfortunately, this could happen and it could have crashed on the oncoming traffic, but luckily it didn't happen. So the bottom line is that, there are lots of complex behavior going on when there's no traffic control, there's no management going on at the site. Therefore, just the drivers are trying to do their best. They have to get somewhere, right? We are all late usually to get to where we want to go. And, taking a detour, is not really a preferred option. So we tend to take risk, and then that could be disastrous. As we saw, in one vehicle got stuck, there could have been a crash, things like that. So it's really important to kind of study these and perhaps take actions to mitigate them. All right, so to just summarize what we covered so far, these image-based approaches look promising for creating a scalable solution for monitoring roadway conditions under recurrent flooding. So we could use these approaches for both predicting the extent and the depth of flood water. However, there's a lot of variety in terms of the image quality, the lightning condition, the site conditions, and the types of flood water we are dealing with. So we need really robust models and techniques before these are usable by public agencies, because we have to establish a certain level of reliability before this could be really integrated into existing solutions. So under partial flooding, the roadway capacity could be dramatically reduced under recurrent flooding, and we need more data to establish a relationship between what the capacity is and what the depth and extent of floodwater is. So I showed you one example under one type of condition. We need a lot more to really look at the whole relationship between at the different ranges, how different levels of flooding affect the roadway capacity. In terms of safety aspects, we saw a lot of chaotic behavior of drivers as they were trying to traverse this partially flooded segments. There's definitely a lot of safety concerns, and we need to come up with effective ways to communicate the risk to the driver. As we are doing that, we have to balance safety and efficiency. Of course, the safest option would be just closing the road, but that doesn't really work very well for the mobility aspect. We do want to provide service. We want to keep the roads open as long as possible. So what's the right balance, right? What's the optimum point where you want to make those decisions? And for that, we need data. We need to build these models, make them more reliable and effective to support such decisions. So with that, I'll conclude and try to answer any questions that you may have.
Thank you, Mecit. Yeah, we actually have a question ready to go, and sure. It's from John Klink. It's interesting because it was what I was going to ask. How about that? About how many images do you need to train the AI or machine learning to get a reasonable estimate of depth? This also came about where I saw someone put a scale in the photo frame at like a stormwater outfall where there was water. So they were getting all the way around the pressure transducer sonar measurement of water level.
Yeah, like a staff gauge.
Yeah.
Okay, yeah, that's a solution. Yes, for sure. Yeah, I think the more the merrier. That's the general rule. The exact number, it's hard to say. 1,000 images is enough. So it's a combination of factors. So if you are using, let's say, a big AI model, the ones like I showed you earlier. So we are using pre-trained model. These models are trained, as a matter of fact, on millions of images. So we don't have millions of labeled flood images. So what we do is we transfer the knowledge these models extracted from existing data sets, because there are common features, like an image taken, for a different reason has certain features that are still useful for flood detection. So we take these images, these big models, and keep their existing parameters, but modify, let's say, the last layer or a certain aspect of them. Therefore, we could we can do the work with fewer images. As we illustrated earlier, with 250 or so images, we were able to get 90% or so accuracy. So the question, it's a great question, but it just depends on the type of model we are using, as well as the type of problems being solved. So more specifically for depth estimation, we would like to cover a lot of variety. Like if all your data is coming from one, you may have 1,000 images, but all of them are from one depth level. So that's not enough, right? We would like to have a variety of images collected under different conditions, so that when you apply this in real life, the model has enough richness in it to capture, what else could happen in your data. So usually want to interpolate, extrapolating is difficult, even with regression, right? Like you have data collected in a certain range. Within that range, your model works really well. But if you try to extrapolate, it may or may not work. There will be non-linearities and all that. So the same is true with these more sophisticated models. So the question, the correct answer is the more the better. But the better, putting a number on it is not really possible, unfortunately. But it's a great question.
It looks like Lauren Summers has a question. Lauren?
Yeah, it's more a comment than a suggestion. I am happy to see that some people are that you're looking at actual lanes and how they vary, because I've seen other projects where they just go, oh, there's this much water, close the roads. And it's nice that this is actually taking into account what people would do. Yeah, one lane may be blocked, but if the other 5 are working, we're not going to close the road. Yes. And I just think it's really nice that you guys are taking that into account, like lane 1, lane 2. It's nice to see. And with that, I know even on Hampton, on that area, I've seen cars floating around. How could we even close certain lanes of that road? Do you just put cones way sooner? How does that work?
Yeah, that's a good question. Like here, for instance.
Yeah, because it fell over, the sign.
Yeah, cones, might be an option. Or they have these trucks, the service trucks. They may come and park here perhaps and have a sign in the back, and just to block these two. Could be different ways to accomplish that, to manage the traffic. Cones is an option. Maybe the bigger cones. We don't want these tiny cones, and there will be wind and all that. But it's a difficult thing. It's definitely, we do not want to close the road. Another problem is you may close the road maybe to passenger cars, sedans, but not pickup trucks and SUVs and minivans and trucks. So there's a lot of variety, and there's nuance. And that's what we want to understand, because, it's not a simple problem, and just shutting down the road is not a solution, right? And that's what I said at the very beginning. You want to look at this specific problem, because there is a lot of literature, other things been done, just looking at the impacts of flooding, but not at this level, because to make it operational, to support decision-making for the cities to make those decisions, they need to know, they need to know the depth and extent at the accurate level, plus minus maybe 1 or 2 inches, right?
Mm-hmm.
So if you have that kind of nuanced data, temporally and spatially, then it will definitely be very useful. And that's what we are after.
And then I have one other question, and that was with that car who was going on the opposite side, like driving the wrong direction. Does that affect your AI at all? Like, do you have to throw data like that out? Does like, what happens when it sees it going like the wrong way? I don't know.
Yeah, that's, yeah, there are, as a matter of fact, there are some projects where they try to detect wrong way driving. This is relatively easy for the AI algorithm to detect wrong way driving, actually.
Mm-hmm.
But if you never thought of it and never incorporated it in your model, then it can throw an error, of course. Yeah. But you have to be diligent and kind of consider this possibility that somebody might be driving in the wrong direction.
So I guess if we really want to screw up AI, we'll start doing like donuts in the middle of intersections.
Yeah.
Large circles, and then see how it does.
Yeah, that's always, this is challenge. Yeah, new data, something never seen before, and then just doesn't know what to do. Yeah, exactly. Yeah, they are not as smart as we think they are.
Okay.
Thank you.
Thank you.
I think John might have had a follow-up question. Is that right, John?
Yeah, I'll go ahead and do it in person. I just was curious, as a follow-up to the number of images, does it help to have a sequence of video images that are related to each other, or does that just throw a bunch of noise into the system that causes a problem? And then, do you have to subset the video so that you get an image every 10 seconds or so instead of every image, the what is it, 24 frames per second that you're getting out of video? So I'm just wondering how time sequences of information helps or hurts these AI systems.
Yeah, it's a very good question. Actually, time sequence data is very valuable. And that's what we were able to do here. With the edge detection method, we were using like 10 or so images, like a sequence of images to be able to look at the movement of water here. Because you just take one still image, it just doesn't tell you like what's happening in terms of the movement. So when our next kind of goal is to work with video data rather than just these still images.
Right.
And we are going to basically like take these videos, identify vehicles, these dynamic objects, remove them from the scene, take some averaging, or apply these filters, and so that we can more clearly detect the boundaries of floodwater. Yeah, but that's a very good question. Yeah, for sure. When you have a video, and furthermore, if the camera is fixed position, that makes things a lot easier because you are dealing with the same scene. Right. And so far, we trained our models with like images taken from any angle, from any city in the world. So that's a lot more variety, more difficult problem to solve. But yeah.
Yeah, in analogy with humans, I know we all do better rather than just seeing a snapshot, rather than, seeing a sequence of images, and our brains are able to figure out what's moving and what isn't. So it would seem the AI should have that similar capability. Anyway, thank you for the answer. I won't ask for a continued response. Thank you.
Thank you. Yes.
I guess I'll throw one in here. I'm kind of curious where you're heading with your computational infrastructure. So as you go to video, you're going to get a lot more data. Are you going to be running these in the cloud, or a cluster on campus or desktops?
Yeah, that's good. For the research purpose, we usually use our own infrastructure, or like the cluster on campus or our own desktops. But to implement these for the cities, like in real life, then there are mainly maybe three approaches. One is like edge computing. You can, some of these models are, of course, they're big models. You need heavy computation, but you don't need to really transfer all this video data to a site to process it. There are algorithms and hardware that will help you run them on site. As these images are coming in, we don't need to preserve all the color and the entire sequence of images. We can just extract features and then process them and then just send the result to the center. essential. That's one approach where all the computation is done, or the heavy computation is done at the edge device or at site, on site. The second approach is, on the cloud computing, you transfer all the video data to a cloud service and do the computations there. The third option is, you can, if the city has enough infrastructure, perhaps their own service can handle it, but usually that's not really possible because of the immense amount of data to be processed. These are, I don't know if I answered the question, but for our research, just for now, we are doing everything within our,
seems like that's
audio
good.
resources.
Potential convergence there with like more, we're getting more higher resolution satellite imagery, drone imagery, and there's an effort to maybe develop a data cube beyond, remote sensing data. So there could be a connection there.
That'd be great,
Hey, Lauren, did you have a follow-up question?
I did. It was regarding edge detection, and how much more challenging is it if like cars are constantly driving through? Because it seems like the edge detection would be much harder if there was a constant stream of vehicles.
Yeah, that's a good technical question, correct. But luckily, we have a lot of these deep learning models that are very good at detecting vehicles. So like here in this image, you see, this is like from a video frame, one of the video frames. So we can, it's not perfect, of course, but if we can like extract these pixels and throw them away, if we are not interested in the vehicle itself, we can identify them relatively well with these methods. So we can just remove them, remove the dynamic objects, these vehicles more specifically here, and then focus on the roadway surface itself. Again, if you have a fixed position camera, then it's really easy to detect like where the road is and the edges or all these lanes, because you have tons of data. And you also have data from dry days and, where just exactly, where the road is. So you can kind of focus your attention there. And, as you have a flood event and you activate the system, then it will hopefully tell you where these boundaries are, these boundaries accurately, where the flood is. Then you take actions accordingly. Like here, for instance, with this model.
Okay, so do you guys have plans of ever using a non-stationary camera? Like what would be where would we want something that's not stationary?
Oh, okay. Like the other apps, of course, now with vehicles are coming with onboard sensors, like especially, the newer vehicles, they have their own cameras. Those that have advanced driver assist systems, they would have like a LiDAR even, a radar and cameras. So another option would be tapping into the camera feed from the vehicle, which is moving around everywhere, right? That would be, of course, another possibility to extend the work where we have this mobile camera and then from those images, try to extract where the flood water is and what the road conditions are.
Yeah, it's really interesting. And then my last little question is, who named the thing you only look once?
Oh,
was that a student?
No, it's not actually our work. It's a well-known model. My student is probably online. He can answer that question.
I just thought it was really funny.
Yeah, it's not you live only once. It's you look only once. Yeah.
I just assumed it had to be a graduate student who would have named that.
What is that? Sorry, I'm scrolling too many times. Yeah, this model. Yeah, there are so many versions of this model now. It's a very well-known deep learning model, and it's very effective. It's not as computationally heavy as other ones. I don't exactly know, unfortunately, who came up with that.
Yeah, I was just wondering.
Well, that stands for you only look once.
Yeah. She was asking who came up with the acronym.
Oh, that's many years back. Those who collected the data.
It was a joint effort between Facebook AI Research, Allen Institute for AI, and University of Washington. You can find the original paper on archives.
Thank you, Iris.
Wow. Well, folks, it's been really interesting. I think after this, I advise you to I don't know, maybe it's Waze or the next evolution of this. But thank you very much, Mecit.
Thank you.
Really interesting, and just opens up lots of other avenues for research. Even the social psychology that you're showing is pretty wild.